A single strand of glass, thinner than a human hair, now forms the invisible backbone of our modern world. Every time we speak to a friend across the distance, our voices are converted into pulses of light, channeled through these remarkable fiber optic threads. Though they appear delicate, these filaments possess a strength for carrying information that surpasses even steel. The creation of each fiber is an intricate journey, beginning with pure quartz sand and ending with massive cable coils laid deep on the ocean floor. It is here, inside state-of-the-art production lines, that millions of these fibers are made, forging the essential framework of the connected age. A single thread of glass, stretched across an ocean, was about to connect humanity in ways once thought impossible. The United States was the first nation to undertake this challenge, and in 1988, the TAT-8 line came alive, linking America with the United Kingdom and France. That moment marked the dawn of a new era in global connectivity, establishing the US at the very heart of the world's burgeoning internet infrastructure. This monumental leap was fueled by American technology titans like Google, Meta, and Microsoft. These companies were not merely users of the network. They became its primary investors and builders. They poured resources into co-owning the most critical data arteries on the planet, shaping the digital world we know. Without these fragile strands of light, it is difficult to imagine what our modern lives would even look like. It begins not in a sterile laboratory, but in the raw, open earth. The creation of optical fiber starts with a specific kind of high-purity quartz sand, sourced only from the most select deposits of white sand that contain the precise concentration of silica needed for optical-grade glass. At the mine, powerful tracked excavators tirelessly scrape away immense layers of the earth. They methodically load this raw material onto massive haul trucks, each one carrying dozens of tons on the short journey to an adjacent processing facility. Once there, the sand cascades onto conveyor belts and travels through vibrating screens, which skillfully sift out larger stones and unwanted organic matter. From the screens, the material is funneled into vast industrial washing tanks, where powerful jets of water and mechanical agitators churn the mixture, scrubbing away stubborn clay, fine dust, and residual vegetation. This intensive washing cycle repeats multiple times, ensuring the entire batch achieves a meticulous standard of purity. Even the wastewater is carefully managed, flowing into a recycling system that reclaims fine silica particles and minimizes any loss of the precious material. After meeting these strict requirements, the purified sand is thoroughly dried in industrial furnaces to eliminate every trace of moisture. Finally, the sand is packed into sealed containers, prepared for the complex chemical stage. Here, its silica will be transformed into gaseous or liquid compounds, the essential building blocks for the glass preform that ultimately becomes optical fiber. It is a substance born not from molten sand, but from an invisible cloud of vapor. From sealed containers, pure silica is transported to a chemical processing area where technicians orchestrate a transformation, converting the solid material into gaseous compounds. Subjected to extreme temperatures, these gases react and condense, building layers of exceptionally pure glass. Rather than melting sand into a single block, this method constructs the glass molecule by molecule, systematically stripping away nearly all impurities. The entire process unfolds inside a hollow glass tube, rotating slowly as a moving torch bathes it in heat. As the gaseous mixture flows through this inferno, it crystallizes into microscopic silica particles that settle onto the inner wall, forming the desired structure. By precisely adjusting the gas composition, engineers dictate which layers will form the light guiding core and which will become the protective cladding. Every layer is controlled with exacting precision, as the smallest deviation in thickness or purity could cripple the fiber's ability to transmit light. These stringent demands make preform fabrication the most expensive phase of production. The raw materials must achieve near-perfect purity, and the deposition can consume dozens of hours for a single preform, driving costs far beyond any other step. After many hours of this continuous buildup, the hollow tube solidifies into a dense, solid rod known as the preform. A typical preform stands between 3 and 6 feet tall with a diameter of a few inches, yet it already contains the complete core and cladding structure, merely on a much larger scale. Once complete, the glass preform is transferred to the fiber drawing tower, a steel monolith rising over 60 feet into the air. At the tower's apex, the preform is secured and lowered into a specialized furnace where temperatures climb to nearly 3,600 degrees Fahrenheit, hot enough to liquefy the preform's lower tip. As the glass begins to yield to gravity, a small droplet is drawn downward into a delicate strand, initiating the continuous production of fiber. From this moment, the entire system operates under meticulous control. The strand is pulled straight down, emerging with a diameter of only about 5/1000ths of an inch, a thread thinner than a human hair. The challenge is maintaining this uniformity from beginning to end, as the fiber's capacity to carry light could be compromised if its thickness wavers by even 1/1000th of an inch. To ensure this precision, a series of laser sensors positioned along the tower continuously scan the fiber, measuring its diameter with microscopic accuracy. During the draw, operators may use pliers or small blades to touch or cut the fiber directly. This intervention is crucial for removing the unstable initial section or for snipping a sample for rapid microscopic inspection. They might also sever the fiber at the end of a run, separating the finished product from the machine and ensuring only fiber meeting the highest standards proceeds. This drawing process can continue for hours from a single preform. From a rod just a few feet long, the factory can spin out optical fibers stretching for dozens of miles, all with unwavering quality and purity, ready for the next phase. After being drawn into a continuous strand, the raw glass is still incredibly fragile. To fortify it for the journey ahead, the factory applies a protective coating almost instantly. The fiber glides through a small chamber filled with a liquid polymer, specially engineered with multiple layers. An elastic inner coat prevents cracking when the fiber bends, while a harder outer shell defends against impacts and abrasion. Immediately after, the fiber passes through an ultraviolet curing system. The intense UV light hardens the polymer in a flash, transforming the liquid into a transparent protective armor. This step is perfectly synchronized with the drawing speed, guaranteeing the coating has a uniform thickness and a solid bond. With this shield in place, the optical fiber can now endure handling, transport, and testing without risk of damage. Once the protective coating is applied and cured, the fiber is guided through a series of automated inspection stations. Laser sensors vigilantly monitor its diameter and uniformity, while optical devices gauge its signal transmission capabilities. This continuous quality control happens all along the line, confirming the fiber's stability before it reaches the winding stage. In the winding area, the fiber is fed onto massive reels positioned at the base of the tower. Each reel is capable of holding dozens of miles of fiber, wound at high speed under constant, steady tension. The entire winding system is meticulously programmed and monitored, because if the fiber is pulled too taut or overlaps unevenly, it could crack or deform. A mechanical arm guides the strand back and forth, laying each loop neatly beside the last in uniform layers, like winding thread on an industrial, monolithic scale. Operators keep a close watch on display screens showing tension and speed, prepared to intervene at the slightest anomaly. When one reel fills, the system automatically splices the fiber onto an empty one, allowing production to continue without a single pause. In this manner, One preform yields continuous reels of fiber, which are then packed into protective containers for safe transport. From the spools of coated and tested fiber, the factory now begins the cabling process to create the final, robust product. First, multiple reels of fiber are set up in parallel and fed into a colossal cabling machine. Here, the individual fibers are gathered into bundles, which can range from a few dozen to several hundred strands depending on the required data capacity. Between these bundles, engineers introduce reinforcing elements made of steel or Kevlar to boost mechanical strength. Kevlar is especially prized for this role. It is lightweight, yet possesses a tensile strength many times that of steel. Next, the entire assembly is encased in additional protective layers. An outer plastic sheath acts as a barrier against moisture while providing insulation, and the cables are also infused with a water-blocking gel to prevent leakage and protect the signal. For undersea applications, the construction is even more formidable, with multiple layers of steel wires wound tightly around the bundle to endure deep-sea pressure and resist damage from ship anchors or seismic events. The machine operates with a precise rhythm, twisting all the components evenly around the fiber core to ensure uniformity across miles of cable. Operators carefully track the tension and winding angle on their displays, knowing that any misalignment or excess compression could cause the cable to fail when bent. It carries the world's data in a flash of light, but before it can connect continents, it must be stretched, frozen, and crushed. Once the cabling is complete, a grueling series of trials begins, designed to prove the product can perform flawlessly for decades. The initial phase involves basic mechanical and environmental ordeals. The cable is subjected to intense stretching, bending, and twisting to verify its strength, then sealed inside thermal chambers that cycle between deep cold and extreme heat. Others are submerged in high-pressure tanks, simulating the crushing weight of the deep sea. Next, engineers conduct optical tests, sending a laser beam through the core to measure any loss of signal, a process that quickly exposes production flaws or substandard materials. To truly prove the cable's readiness, however, it must undergo full-length testing. Technicians connect both ends to optical transmitters and receivers, sending a continuous stream of data for hours. This is not just a simple pulse of light. The system transmits video, voice, and network traffic, perfectly mimicking real-world operation. If the signal travels the entire length without packet loss, distortion, or unusual attenuation, the cable is one step closer to approval. It is also run under a continuous load for extended periods to test its long-term stability. Select samples are even installed in true field conditions, buried underground or strung from utility poles, their performance measured again after days of operation. Only through these real-world trials can the manufacturer be certain the cable will withstand 24/7 use for many years. After passing this gauntlet, the spool is officially a finished product, but its journey is far from over. It must now navigate the equally critical stages of packaging and transportation. At the factory, the cables are carefully removed from the testing machines and mounted onto large rotating shafts. From there, they are rewound into immaculate coils on massive drums of steel or reinforced wood, each one measuring several feet in diameter and capable of holding hundreds of miles of continuous cable. This winding process is performed with extreme care to avoid excess tension or sharp bends, as even a minor kink could degrade the signal. Once coiled, the cable ends are sealed with protective caps against dust and moisture. Every drum is then meticulously labeled with its batch number, length, structural type, and inspection results, followed by a final check to ensure the spools remain secure for movement. For transport, the drums are loaded onto heavy-duty trucks or into specialized shipping containers. When their destination lies across the ocean, They are placed aboard massive cable-laying vessels, specialized ships equipped with multi-deck storage for dozens of these giant drums. Steel securing systems lock each drum in place, preventing any movement during voyages that can stretch for thousands of miles. This entire process ensures that every spool leaves the factory in perfect condition, ready for deployment in projects that span bustling cities or lie deep along the ocean floor. It is a thread thinner than a garden hose, tasked with surviving the crushing pressure of the abyss. From the port, responsibility passes to specialized vessels known as cable-laying ships. On board, massive drums feed the line into the sea, guided by tension control devices that prevent it from bending or breaking on its journey down. The process is deliberately slow, just a few miles per hour, as the ship traces a precisely surveyed route across the ocean. In the deep, the cable is simply laid upon the seabed, but near shorelines it must be buried for protection from anchors. Underwater plowing machines carve trenches, settling the cable several inches below the seafloor. Engineers monitor this entire descent using sensors and cameras, ensuring the line is laid straight and without any twists. At last, the cable rests securely on the ocean floor, a silent link between continents that forms the very backbone of the global internet. It travels the globe in less than a second, a silent pulse of light. But its creation is a journey of staggering complexity, a testament to human ingenuity connecting the world. The process transforms pure white sand into cables destined for the deep ocean floor. Every single meter must pass through dozens of demanding steps, from purification and fiber drawing to coating, cabling, and testing before specialized vessels can lay it to rest. The final result is a vast highway of light, enabling billions to communicate, learn, work, and enjoy entertainment with a simple click. A call spanning continents connects in under a second, and the movies we stream arrive on our screens almost instantly. What feels so ordinary in our daily lives is powered by one of the most intricate industrial processes on Earth, a hidden world of creation that most people will never get to witness with their own eyes.